Welcome to you, Leila Schneps. Yes, hello.
Good to see you.
I'm just getting a call from Nitsure. Hello. Oh my God. अच्छा अच्छा हाँ म्हणजे that we can do पण ते म्हणजे तो झूम मीटिंग स्टार्ट करून ते गुगलवर जातो म्हणजे झूम मीटिंग चालू केली झूम डाउनलोड करतो ना आपण झूम मीटिंग डाउनलोड करून अच्छा हाँ तो प्रॉब्लेम काही जण नव्हता हाँ अच्छा म्हणजे रजिस्ट्रेशन हाँ ते रजिस्ट्रेशन ते काय केलंय रजिस्ट्रेशनची एक लिंक आहे तर यू हॅव रजिस्टर्ड अर्लियर अच्छा आणि युजर आयडी पासवर्ड काय उपयोग होत नाही दॅट्स व्हॉट यू आर सेइंग Hello, Mr. Sommede. Sommede is here. Actually, Nitsure is unable to join because that link doesn't work somehow. I mean, user ID, name, password. It is asking many questions and ultimately it is not connecting. So that user ID and password business is not enough or something, we don't know. Those who are not registered already, for them.
So if he has already registered, he must have received one email from Zoom. There is a link there. You just click on there. It's a one-click process.
Now, have you registered already for that Zoom meeting? Then there should be. अच्छा. So okay. Soumya, is it possible for you to send some link to Professor Nitsure? Yeah, then it's okay. Okay, no problem. No, that is different, but in any case, sometimes.
I thought I will say hello to you, Professor Leila Schneps. I am Deependra Prasad.
Hi. That is okay. That is no problem.
I am Deependra Prasad.
Oh, right.
Yeah,
Oh, hi.
I am Deependra Prasad. I am usually based in India, but it's possible I have met you at some point. I'm not sure. You are based in France. You are in France?
That's right. I'm in London right now, but I'm based in France.
Okay.
Why this doesn't work, etc.
No, you have been pursuing this very beautiful subject, Deja Dafa, and you are partly going to speak about some of the historical moments.
Okay.
Yeah. I'm going to try and put that in context.
Okay. I have heard that you knew Grothendieck very well.
No, very well. Let's say I met him only twice, but we wrote many, many letters to each other. So in
Okay.
some way.
You met him only twice?
Yeah, I met him twice, but each time for a long time, very many hours. But then it was just letters.
Okay. You were based in France then?
Oh, yeah, I've been in France for 40 years almost now.
Okay, so
Long
notes of the
time.
letter exchanges were between.
After we met, we started to correspond.
Okay. All right. No, he is one of those enigmatic figures in.
He didn't wish
of-
to be visited, in fact. So I actually returned to see him more than once, but he didn't want to see anyone.
Even to you, he did not wish to see?
After the first 2 times, he was very welcoming, but then no. And
Which
sometimes
year-
he stopped writing for long periods, even years, and then he would again start writing. It was very complicated.
because he would relate your visit to some other people whom he would not want to be seen divulging his whereabouts.
Yeah, he asked me not to. So for many years, I didn't tell, but it wasn't. Other people managed to find him. If you really want to find someone, you can do it.
I see. No, because, you know, I was reading these letters of Mumford Grothendieck correspondence, and I think till mid 80s, he seemed like doing okay.
Yeah, he actually chose to disappear in 1991.
Ah, okay.
It was a
okay.
very
So
special year. He
for
left.
a long time, he was okay.
Yeah, anyone could go see him. He was quite friendly.
Till 91.
Yeah. And then suddenly he decided to leave everything and he disappeared, really. He left all his mathematics papers, everything, his whole house, just left, went away. He took only his car.
He quit IHES about 1971, 72.
Yeah. But this was 20 years later.
So for 20 years, he was in this
he was
place
near
in
Montpellier. He was teaching
Montpellier.
Montpellier. Then he retired. He was still living near Montpellier. And then
Okay.
he left suddenly, completely disappeared.
91 or so.
Right, that's right.
Okay. Is somebody writing a biography about him?
Yeah, there are many. There are several now. There's one by Winfried Scharlau. I don't know if you've seen
Yes,
it.
Charlau. Okay. No, I know. Perhaps I have seen something or the other. So he has written about.
None of them can really be said to be complete. There's a few more that came out in French. They're by journalists. They're not very good, but you know, if you read enough, he wrote a lot about himself. That's really the thing to read.
He wrote a lot about himself.
Yeah. If you can read French, that's the most. He wrote very well, extremely well. I love
I was, because of this correspondence between Mumford and Grothendieck, I was inspired to go back to this recalled ASMI. So I think but he writes a lot.
They're going to publish this now after many years. Finally, that book will be published.
Oh, it's coming out?
Yeah, it's coming out.
The one that I saw is about 200 pages. That's all?
Oh, no, I think it's much more than that.
So maybe it's just one part of it. So
I don't know. I haven't seen the book itself. They say they haven't shortened it at all. So we'll see.
Hello. So we have to start the talk now. So I request Professor Leila Schneps, can you put on your PowerPoint if it is there?
Can I what?
Slides. Yeah, slides, your slides. Would you be putting your slides, presenting those? So
can you see them or should I do share screen?
We do not see that. You have to share screen for that.
Oh, I'm sorry. Let me do share screen.
Share screen, yeah.
That's right. Sorry. I need to make some permissions. I hope this is, yeah, it should be okay. Let me try now.
Yes.
Is this
We
working?
are seeing that. Yes, it is working. We are seeing that.
Okay.
So, well, we can now start the talk. So,
Okay.
we are very happy that Professor Leila Schneps is here with us, and she will give a talk on Grothendieck's path from topology to arithmetic, Dessins d'enfants, and the game of Lego Teichmüller. So, over to Professor Leila Schneps.
Thank you very much for this invitation. I'm quite excited to be speaking in India for the first time, if I may say so. So I listened to the previous talks that were given about the Dessins d'enfants and the Bialy map and the calculations of Bialy covers. And I'm going to just take 1 minute before I start my talk to tell you what I'm going to try to do. It's a very, very ambitious talk. What I want to be at the same time very quite vast and give a big overview. And I also want to be quite precise and connect up with everything that you've heard about the Dessins d'enfants so far. And my main goal is to place the invention of Dessins d'enfants by Grothendieck in the framework where he came upon them and introduced them and explained to you why he was interested in them and what he wanted to do with them. So Dessins d'enfants themselves were studied in different contexts by different people. It's not a discovery that he alone made, but the connections he made and the purpose, the way he arrived at them and why, that's what I'd like to give you a view of. So I'm going to be telling you quite a bit from the original. So I'm basing myself on this text that Grothendieck wrote. He wrote it, it's called Sketch of a Program. And let me tell you a little bit about this text, Sketch of a Program. He wrote it in about 1983 or 4. And he had been thinking a lot about various aspects of Galois theory in his own way for the last couple of years. And at a certain point, he decided that he had been teaching at the University of Montpellier then for quite a long time. He arrived there in about 1973. And he was quite tired of teaching. He was actually quite discouraged. He writes this in the Sketch of a Program. He says that he did his utmost to really capture the students' attention, to interest them deeply, and he wasn't succeeding. And he thought that he would ask the French Research Institute, the CNRS, to give him a position for the last few years of his career before retirement. And when you apply for a position to the CNRS, you have to give a research program. And that's what this usually it's about 10 pages long. His is more like 60 or 70 pages. It's extremely beautiful and inspiring. And it's filled with ideas. It doesn't resemble the way Grothendieck wrote math that you know of at all, which was actually perhaps mostly written by Dieudonné, the EGAs and even the SGAs. It's something completely different. There are no theorems, there are no definitions, there are no statements. There are just ideas and visions and what we could do and what we should try. And I believe this structure, and I think we must have that structure, but it's not very explicit. It's a very, very beautiful and inspiring text, which I myself discovered in about 1991, and it inspired me immensely. And I'm going to show you quite a number of quotes from it among my slides so that you can get a flavor of the way he writes. I've translated them into English, but, respecting his style and his way of writing. So to get back to what you saw in the previous talks, we've seen all these notions, right? I made a word cloud here. All these things that are associated with Dessins d'enfants. And I know that although Claire mentioned briefly at the end of her talk, the absolute Galois group and the Galois action, but that didn't get a lot of space in what you've seen on Dessins d'enfants so far. But it was a major, major motivation of Grothendieck. It's really the angle from where he was coming from. So I'm going to go back over all these notions that we've seen already in the previous talks, but I'm going to be placing them in the context of what he was trying to do, which was approach using these very topological objects a completely number theoretic question, which is what how can we study the absolute Galois group of the algebraic numbers? So I'm going to remind you of lots of things I'm not going to be very detailed because we've seen plenty of talks on these and we've had all these definitions very clearly. So this will just be quick reminders. Just have the picture of the Dessin d'enfant in your mind. You have a topological surface of some genus G, and on it, you've got a graph, and you have very few properties that this graph needs to satisfy. One is it needs to be bipartite, so you can color all the vertices alternately in two colors without any of the same color being neighbors. And the other is that when you cut along the graph, all the pieces that you obtain have got to be open cells. You can't have anything with a higher genus or cylinders. And what's below that is what we've already seen. I'll go over it again quickly. I'll explain it maybe in my own way why it is that you have this, but to every dessin, there's associated a unique Bieli cover. And this, of course, is where things get exciting because a dessin is a totally topological object with no rigidity at all. But a Riemann surface is a completely geometric object, which means it's quite rigid. And there's a whole geometric content encoded in the purely topological data of the dessin. So when you have the Bieli cover to get the dessin is very simple. It's just the pre-image of the segment 0, 1, the pre-image of 0 and the pre-image of 1, those are the 2 points over which you can have ramification. So there may not be the full number of pre-images over those points. Those are the vertices of the dessin. But the number of edges, there's no ramification in the open interval 0, 1. So you have the number of edges, that's just the degree of your map. And if you, instead of taking just the segment 0, 1, you take the whole real line, we call it the full dessin, and it's something that you've also seen in one of the previous talks. I think that Claire also showed this. You triangulate your dessin. The way to do it is you simply add another point in every open cell, anywhere. It's all topological. There's no structure. So just somewhere in every open cell, you add another point with a different color. I usually put a little star. And then from every vertex of the dessin, you draw the touch that's surrounding that open cell, you draw a new edge to that point in the center of the open cell, and this completely triangulates your surface. And the full dessin gives the dessin just by erasing, the new colored points in their edges, and the dessin gives the full dessin. They completely determine each other. But the triangulation is quite useful for certain things, as we will soon see. Okay, so I guess the really key point that for Grothendieck, which wasn't stressed all that much in the previous talks, is the arithmetics of the situation. The arithmetics of the situation come fundamentally because if you have a finite extension of P1 and the ramification is all over points that are defined over Q or Q bar, then the curve itself is going to be defined over Q bar. And when something's defined over Q bar, you have a tremendous richness of arithmetics going on. You have a field of definition. You've got a Galois action. You have all kinds of things coming in that suddenly have to do with the algebraic numbers. So all of this seems like basic math, but it's kind of, if you just think of this very simple thing, if you have a dessin d'enfant, you have a Bieli map. If you have a Bieli map, you have a curve X. The curve X is going to be given by equations. It has a field of definition, which is a number field. So if you just think, to a dessin, there's associated a unique number field. It's already an extremely surprising statement. And that is the kind of surprise that Grothendieck really, really appreciated. Grothendieck actually very much believed that topology, geometry, arithmetic, dynamics, analysis are different languages, but they're not at all disjoint subjects. They're very far from disjoint. They may not all be telling us the same things, but there's a huge overlap. And that very often you can talk about the same thing in these different languages. And if you can go from one to the other, if you know the bridges, one will give you information about the other. But this is something that nobody had tried to do before Grothendieck, is to study the utmost arithmetic object that exists, which is the absolute Galois group of the algebraic numbers, by using topology. So that is the fundamental idea that he had. And what sparked it is the realization about all the the geometry and especially the arithmetic contained in Dessins d'enfant. So here's the first quote from the Esquisse d'un programme, which I'm giving you. This discovery, which is technically so simple, made a very strong impression on me. So the discovery, of course, is that to a dessin, there's a Bialy map, an associated Bialy map of Riemann surfaces. And it represents a decisive turning point in the course of my reflections, a shift in particular of my center of interest in mathematics, which suddenly found itself strongly focused. I do not believe that a mathematical fact had ever struck me quite so strongly as this one, or had a comparable psychological impact. This is surely because of the familiar non-technical nature of the objects considered, of which any child's drawing, scrawled on a bit of paper, at least if the drawing's made without lifting the pencil, gives a perfectly explicit example. So here are some Dessins d'enfant for you. I want to mix the math that I'm going to be showing you in this talk with some actual remarks about Grothendieck, the way he thought, the way he was in general, and also what he was trying to do in this situation. But it's a very well-known fact that Grothendieck was probably the most abstractly minded mathematician who ever existed. The mathematics he did, his whole approach to math, even when he was young and he was working on topological vector spaces and all through the different areas of mathematics that he covered in the 21 or 2 years that he really worked on math, he always had the same approach. It's like a signature. He would look at what people were studying, look at what they were doing, and he would try and distinguish between any feature special to the actual object they were looking and any axiomatic property that could be completely general. This is completely like the signature of Grothendieck's approach to math. Just to give you the example that everybody knows, when people were studying algebraic varieties, he really introduced the importance and the necessity of studying schemes. He wanted to lessen the number of hypotheses that you have to take on the rings that people would study. And basically, he was, why are you studying only certain types of rings? Study the most general possible type of rings. Study any rings. Take away this hypothesis. Take away that hypothesis. Take away no theory. Take away the hypotheses. Just use the most general situation. And on the one hand, when he did this, he of course lost what most mathematicians really need, which is the constant recourse to examples to make sure that what you're saying is right and has a kind of an explicit form. But what he gained is that he realized that many different situations that people were working on were all really essentially fundamentally the same. And this is kind of the object of the famous article he wrote in Tohoku in about 1955, when he tried to rework what Eilenberg MacLean were doing for himself. And he came on this complete general formulation, and people were essentially studying modules, and he generalized the whole situation. The thing is, the reason he was able to think this way and to make it work was because examples meant very little to him. It's of course very famous that somebody said to him, take a prime number, and he said, what, like 57? So he just, numbers, in a way, I guess you could almost say it was the complete diametrical opposite of Ramanujan, who just loved the numbers one by one like his friends. Instead, Grothendieck had, it's famously said that there's no numbers in Bourbaki at all, except the numbers that number the sections, 1.2.18. Anyway, he did not like examples. He never worked out examples. If he was thinking about a statement and he wasn't sure it was right or wrong, he just didn't seem able to go work out an example. He would call Serre on the phone. Serre was his person to, give examples or counter examples. But the day he somehow came on the idea of Dessins d'enfant, he discovered the beauty of examples. I'll just go forward to, I don't know, maybe we'll come on it later. There is one quote, I think I put it later on in the talk, where he just says, I worked out a few examples by hand. And I wanted to point out how striking that is, because something he never did. The Dessins d'enfant, the fact that they were concrete, that you could actually draw them on a paper and that you could work out, figure out the Bialy map, figure out the explicit Bialy map, the number field things were defined over, and then the Galois action was astounding to him. Of course, he could only do the very tiniest Dessins. It's very difficult. If you want to figure out the Galois action on Dessins, the only way we know to do it now is to calculate that whole Bialy cover. You saw a whole talk on the subject using the Grosvenor basis. It's something that can be done by computer. It's very difficult. You can't do it when the Dessin is too big. There's no actual complete theory. It's just a very astounding thing that the Galois group will take a Dessin and shift around all the edges and vertices and permute them and make another Dessin. But we don't know how that works. And the only way we can even see the result of the Galois action is by going through a full computation of the Bialy cover, using by hand if it's tiny, or using Grosvenor bases if it's big. So that's not a road that he wanted to travel on. He did a few by hand, the little ones. And then he said, well, this isn't the way I want to go. And he switched to what I'm going to be basically talking to you about. However, just to summarize what was said in the previous talks, which you pretty much already have heard, why does a Bialy cover, why does a Dessin correspond to a Bialy cover? I want to say this because I'm going to say it in a highly topological way. So what I'm going to say just proves the existence. It doesn't give you what you need to calculate anything. It doesn't give you the Bialy cover. It just shows that it exists, okay? So it's very simple if you just use the topology. You take your Dessin, so I took that little balloon, and you triangulate it. So I simply added, there are 3 cells there, the outside and the inside of the balloon and the inside of the little triangle. I added a star in each of those. I connected all the vertices to the stars in the cells that they're touching. So now what have I done? I've triangulated. So my drawing's on P1, right? It's on the plane, it's on the sphere, really. So I triangulated the sphere now. And in fact, I've triangulated the sphere with these little pairs of oppositely oriented triangles that all look like this. And you take every one of those little pairs, and you just, like a piece of paper, you fold it over and you identify the white to star edges and the black to star edges. And what have you got? You've just got a sphere. You've just got a sphere topologically with 3 special particular points on it. And to make your cover, you take each pair of triangles, each pair, and you fold them over that way, and you identify them with the sphere with 3 mark points. You just do it in such a way that you take a homeomorphism of each folded pair with P1, identifying the 3 mark points here with the 3 mark points there. You do it in such a way that it agrees on all the edges. And that is a topological map from your topological triangulated surface over to P1 with 3 pinched points that have less pre-images than every other point. So topologically, it's extremely simple to see why a Dessin, or how a Dessin gives you a cover with 3 ramified over 3 points of the sphere with 3 like ramified points. And now it's just a basic theorem that if you have a Riemann structure down there, you now equip that sphere with 3 mark points with the Riemann structure P1 and 0, 1, infinity. You pull that Riemann structure back to, in a unique way, to your topological cover. And that doesn't tell you anything. It doesn't tell you any information at all, except that it exists. But it's not going to tell you anything about how to get the equations which you want, and how to get the coefficients and the number fields and the Galois action. So all I've told you here is the briefest notion of why that cover exists. But so this is something that quite struck Grothendieck. You start with your Dessin. So I drew some Dessin. You can draw it however you want, because it's purely topological. Nobody cares. They're all the same. But when you do what I just did, so you make your topological cover. So now I have just a topological cover of P1 to itself. And it's got these 3 points of ramification. And now I put the rigid structure downstairs, and I pull it back to a rigid structure upstairs, which is still P1. The Dessin is now the pre-image of the segment 0, 1, and it's on P1, and it's totally rigid. You don't have any choice about it anymore. It's really quite funny because, so you can see that the little man is lying down horizontally now. And the reason is because he has a symmetry. He's actually symmetric. I mean, he doesn't look symmetric, but he, for the topological information, he is symmetric. And so he has a symmetry axis along the real axis. So complex conjugation is is an order 2 symmetry of this dessin. And that's why it has to be lying down that way. And all his symmetries have to be respected. Just the fact that, there's a symmetry that exists here, you're going to see it visually on the rigidified dessin. But it's even funnier because, his position is just completely decided. You can't choose. So that's just one indication of the extraordinary amount of geometric information contained in a thing that isn't geometric when you start with. This is exactly the kind of thing that fascinated Grothendieck. So here are the easiest dessins. These may be the ones that he was actually able to completely work out by hand, since these are all the dessins with 3 edges. Since all the ramification indices exactly, you can write down the form that your Bialy function must take. All of them are of genus 0, so it's just a rational function, except for the very last one, which is of genus 1. So, okay, you work these out. Well, there are very, very few dessins with 3 edges. They all have a lot of symmetry. Basically, they're all defined over Q. As a matter of fact, one thing you can do is, if you draw a dessin, so you already heard in the previous talks about dessins, that if Galois acts on your dessin gives you other dessins, they all have to have the same ramification indices exactly. So if you ever happen to draw a dessin with ramification indices, such that there is only one dessin that you can draw that has those indices, then that one's defined over Q. So that at least is kind of cute. If you draw a dessin such that there are only 2 dessins with the same ramification indices, you can't be sure whether they're both defined over Q or whether they're just in the same quadratic Galois orbit. So then you have to go and make some calculations. But sometimes you can see it if there's a symmetry. Okay, so this is just a summary of what I've just been telling you. There's a number field directly associated to the dessin. So this purely topological dessin contains all this other information. The geometric content is very well understood, basic Riemann surface result, but it's still very mysterious because there's such an enormous gap between knowing that it exists and knowing what it is, being able to determine it. And we don't have any good method to determine it or anything about it except, the algorithmic methods. So even in that sense, it's very mysterious. One might say, okay, there's a number field associated with the dessin, and that number field has a degree over Q. That's just an integer. So it's just a very important integer associated to a dessin. Couldn't we read it off the dessin in some combinatorial way? People have worked quite a lot on this question. It's just nobody knows. These are these are very surprising questions. So the fact that you could express certain arithmetic objects, let me say this, it isn't that when you just take a simple little dessin, you have a whole curve defined over Q bar associated to it in a map that fascinated Grothendieck. It's the other way. It's the fact that a hard thing like an algebraic variety and a cover with certain ramification could all be encoded in just little dessin. That was more the direction that fascinated him. He said, but here I have these very rich arithmetic objects that everybody knows, an algebraic variety defined over Q bar, covering P1, certain ramification. Everybody knows the Galois group acts on it. But how can I capture the essence of that action with some invariance, some basic elements? I don't need to write down every single thing, the whole equations of the curve and the map and everything. No, I just need to encode it with some kinds of invariance and say what Galois does to them. That is the kind of thing that he wanted to do. And that's where he really hoped that Dessin d'Enfant would lead in a direction where he could do something like that. So I put in another one of these quotes from Esquisse d'un Programme to show you how incredibly fascinated he was by this result, which already the fact that a dessin was associated to an algebraic curve, well, that he had, of course, understood. But the fact that every algebraic curve can be made into a dessin, that is, you can always find a Bialy map from it to P1 ramified over 3 points only. That's what Bialy proved, which you heard a whole talk about that proof. And then you just take the pre-image of 0, 1, you get a dessin. And it's every single algebraic curve, no matter which ones. This truly he found it just incredibly important. When you read what he writes in this quote, he says here, to me, the essential message of Bialy's theorem is that there's a profound identity between the combinatorics of finite maps. Maps are dessins. By the way, let me just say he didn't call them dessins d'enfant in any like a definition. The expression comes from that sentence that I read where he said any child's drawing is an explicit example. Other people started calling them dessins d'enfant. He himself always called them carte, map. So finite maps are dessins on the one hand, and the geometry of algebraic curves defined over number fields on the other. So this underlined sentence, this deep result, together with the algebra geometric interpretations of maps, opens the door onto a new unexpected world within reach of all who pass by without seeing it. So he was quite astounded. It's something he repeated many times, that Bialy's theorem, I think people really like Bialy's theorem. It's a very pretty theorem. But he seemed to feel that he was the only person to realize that that theorem was like an open door into this, what he calls the profound identity. And that got him very excited because he thought there's a totally new way to study arithmetic now, by using this identification to translate it into this combinatorial topological language. Okay, so what I'm going to do, I'm going to have three parts now in my talk. I'm going to talk about the topology and geometry of Dessins. I'm going to talk about them as covers, essentially. And the reason I want to do it is basically it's going to lead toward, this is a necessary step to lead towards explaining how Grothendieck viewed the Galois action. Now, I'm going to explain to you how Grothendieck viewed the Galois action, and it's not what you might think. You might think, anyone would think, all right, we take a dessin, we want to know the Galois action. We have to calculate the Bialy map by using whatever algorithms we can manage, and we have to calculate the equations for the curve, and then we get the coefficients and their algebraic numbers, and then we get the Galois action. And then we can use the Galois action and write down the image. We take some Galois element, we write down the image of the curve, and then we calculate the new Bialy map, we take the pre-image of 0, 1 under that, we get the new dessin. Grothendieck has a completely different approach to calculating the Galois action on dessins. I'm going to say it to you in one sentence, but then I'll be explaining it to you in the next several slides. So in one sentence, here's what he said. Everyone has always studied the Galois action on algebraic numbers. Let's not do that. Let us not do that, but instead just study, well, we would like to study the Galois action on topological objects like dessins, but we don't know. It's hard. But there's something between the topology and the arithmetic. It's the geometry. We're going to study the Galois action on covers, but we're not going to study it cover by looking at the algebraic numbers that are the coefficients. We are going to identify covers with finite order subgroups of the fundamental group. And we're going to have a huge Galois action on the whole fundamental group that permutes these subgroups. And we are going to look at exactly how the Galois group acts on fundamental group, which are groups that have generators and relations. So that should give us information about the Galois group action and how it permutes the subgroups. So I call this geometric Galois actions. He's not going to have them acting on algebraic numbers. He's going to have them acting on fundamental groups. So in order to explain that, I just have to first explain how to view dessins as subgroups of fundamental groups. Okay, so there are several ways to do it. So the next few slides are really just to bring together different ideas that everybody associates with dessins. All right, so I want to mention the triangle groups, which maybe haven't been mentioned very much now. So there's a definition of a triangle group, very familiar groups. We only consider the hyperbolic situation. So what is a triangle group exactly? You have a tiling of the hyperbolic plane. So you have the upper half plane, the Poincare upper half plane, which is often also represented as a hyperbolic disk. And you have a tiling of it by triangles. And these tilings have symmetry groups, the infinite symmetry groups, which are the triangle groups. So the triangle groups, they have these three indices, P, Q, and R, which are the powers of the generators, the orders of the generators rather, and each value of P, Q, and R, which can also be infinity, each triple of values corresponds to a different triangular tiling of the hyperbolic disk. There's one of them that in everything I always do anyway. It's more important than any others. We'll come on it in a minute. But all of them are valid triangle groups. And this is where the fun thing happens. All you've got here is the upper half plane. And I'm just going to do exactly what I did before with a Dessins. It's paved by these black and white pairs, which are just like the thing I showed you before. You take each black and white pair, fold it over, identify the edges, and what you get, exactly like before, you just get a little P1 with 3 particular points. And you do that with every black and white pair. Like you take the whole tiling by these kite-shaped objects. And each of them you identify with P1 and by a homeomorphism. I'm saying P1, but it's just S1. It's just the sphere. I'm not, it's S2. I'm not using the Riemann structure yet. At this point, I'm being completely topological. So you just have a homeomorphism and you make sure your homeomorphism is compatible just on the edges. And what have you got when you do that? You have a cover, this thing, covering the sphere. It's got 3 ramification, 3 points down there over which there is ramification. All of the ramification over one of the points is all of degree P. Over another point, it's all of degree Q. Over the third point is all of degree R. So it's a bit like a Dessins. It's a little more specific than a Dessins because a Dessins, you have ramification over 3 points, but you don't have to have all P, all Q, and all of R. But it's not essentially different from, well, it's certain Dessins. These are just, well, okay, that's not true. It's not certain Dessins because this is our infinite covers and Dessins are finite covers. But every finite thing between this infinite cover and the sphere downstairs, every finite thing is a Dessins, okay? These are slightly special Dessins because they only have these 3 ramification indices. However, they're enough Dessins to cover all Dessins, and just like you would say, all number fields are not Galois, but all number fields are contained in the Galois closure, and Galois number fields are, if you want to study the infinite Galois group, Galois number fields are enough to look at. It's the exact same thing here. Any Dessins is going to be covered by a Dessins of this type. You just take P, Q, and R to be the least common multiple of the ramification indices over 0, 1, and infinity. And you can find a Dessins that covers your Dessins in the sense that but it's a cover. Okay, so you have these triangular groups. And the Galois Dessins, the regular Dessins whose indices are all over each point are all equal, those are finite covers between this and the sphere downstairs that you get by identifying all the little pairs. Therefore, very simple conclusion, every Dessins of this type, with this limit on the ramification indices, corresponds to a finite index subgroup of a triangle group. Okay, so first, I just want to say something about these points over which we're ramified. This is something very important. I'll be using it through the rest of the talk. I'll be using it all the time. Checking the time. Yeah, okay. How long should I like stop at 2:30?
No, you can for half an hour, maybe
A few minutes
talk.
extra. Okay, well, because I don't want to hurry too much because it's fun, but I don't want to go on too long either. Okay. So we all know that what a fundamental group is, right? When you have something downstairs, you have a surface and you have its universal cover, and the fundamental group is this group that acts properly, discontinuously, and freely upstairs on the universal cover, and then you quotient by that group and you get your surface that you're looking at. And finite covers of your surface correspond to quotienting by finite index subgroups of the fundamental group. Now that situation is almost what we have here, but not quite. We don't have a free action. There are finite stabilizers. When we have the triangle group acting on the upper half plane, some points don't have the right number of pre-images. So they're not carried by every element of the triangle group to other points. There are finite stabilizers there. So what the result is exactly what we've been saying. It's ramified points downstairs. You've got a sphere downstairs, and I say the points are pinched, but of course you can't see anything. They're just 3 points. They're pinched just in the sense that you've got ramification above them. But you can visualize that they're pinched when you fold over those black and white pairs. You can actually kind of see the pinching, okay? So when you have a situation like this, instead of saying you have a manifold, we call it an orbifold. The triangle group is an orbifold fundamental group. We're going to be seeing a lot of those. So it's really just like a fundamental group. It behaves in every way like a fundamental group, and there's no need to, it doesn't create any extra difficulty, but it's just important to know that it's what happens when you admit ramification. Okay, so if you take a finite index subgroup of the triangle group and quotient the hyperbolic disk by that, you get a finite cover of the sphere ramified over 3 points and equipped with the triangulation that comes along with it. And that is the full descent d'enfant. It's exactly what you're getting. So that's one way of seeing descent d'enfant. Now I want to talk about a second way of seeing descent d'enfant, which is, I believe, what was used in the lecture that we heard about Bieli's theorem. So you can do it different. You can consider a descent. So just take your descent and take your Bieli cover associated to your descent. It's ramified over 3 points, but now you puncture the 3 points downstairs. You just take them out, and you take them out, all the pre-image upstairs. You just take them out. So you get a pin, you poke holes in your surface at all the points over 0, 1, and infinity. And now you've got an unramified cover. So this is nice because, of course, unramified covers, they're simple. They're much easier to work with. You don't have these pinched points. You don't have these ramifications. You can complete the thing and uniquely. So you have all the information. But a lot of things become simpler. And in particular, what becomes simpler is the fundamental group. You now have exactly the same information, but you have an unramified cover of P1 minus 3 points, 0, 1, and infinity. And the fundamental group of that is just the free group on 2 generators. And that means that you have a bijection between descent d'enfant and finite covers of P1 unramified, outside those 3 points. So that just a finite index subgroup of the free group on 2 generators. Up to, if you want to use your Riemann surfaces up to isomorphism, then you're going to take your finite index subgroups of the free group on 2 generators up to conjugacy. So conjugacy classes of finite index subgroups. Now this is exciting, okay? Here we're getting much closer to the way that Grothendieck thought about things. Dessins are associated to conjugacy classes of finite index subgroups of the free group on 2 generators. So we're going to get back to that because that's going to play a very important role. But let me say one last thing before we get back to that. This is extremely similar. If you take, so PSL2Z is just a triangle group, just like any other. It's a triangle group with indices 2, 3, and infinity. But it's extremely well known. It's probably by far the most famous of all the triangle groups. And when this acts on the Poincare upper half plane, it triangulates it just like what we saw before. Gives you triangulation. You do the exact same thing. Gives you a cover of P1 with the three pinched points. But what's particularly special about this, extremely well known, is that if you take this fundamental domain, well, people usually pick this one. It's just that one choice of 2 triangles. These are triangles because they all end up at 1 point up at infinity, right? So this whole thing here is really just 1 point. It's the point at infinity, which should be collapsed to a point. This whole area here in the upper half plane parametrizes isomorphism classes of elliptic curves by the J invariant. Just a point here, any point, every single point is the J invariant of a unique elliptic curve, isomorphism class of elliptic curves. So when you do the cover, everybody gets identified with just this one being folded over. Every point in here, like I was explaining before, every point in this gray area is sent by the whole of PSL2Z to points in all these other areas. The ramification points are here. What gets identified is this vertical line gets identified with this vertical line. These 2 points here, this point gets identified with this point, and this point gets folded over. So there's, I think I have a drawing here. Yeah, it's not a great drawing, I'm sorry, but this is that fundamental domain. And you just fold it over to identify this with this, and you sew this half to that half. And here you have your P1, it's got 2 pinched points now, and it's got a little hole up here at the top where infinity is, but still a P1 with 3 particular points. Okay, so yeah, here's how you identified it with a triangle group. So it's nothing different from what I was saying before. Yeah, it looks like the square of this is -1, but it's really 1 because we're in PSL2, okay? So again, PSL2, which is just a triangle group like the others, but it's the really special one because it parametrizes elliptic curves. It gets you, again, to a sphere with 3 special points. And it's got this very, very important subgroup inside it, gamma of 2, which is just the matrices that are congruent to the identity mod 2. And that is free on 2 generators. I just give them here. It's free on these 2 generators. It is the free group on 2 generators. The picture you need to have here is like this. You have the hyperbolic disk triangulated by what I showed you with PSL2 of Z, which is here, triangulated that way. You have PSL2 of Z and you quotient it and you get this funny pointed sock-shaped thing. But between the two, you can quotient it by just this free subgroup. And what you get when you do that is P1 minus 3 points, 3 actual holes. And then to get from the P1 minus 3 points down to the funny sock-shaped thing, which is here, you quotient again by the quotient of PSL2 mod this, which is just S3. It's just the permutation group of 3 points. Permutates the 3 points. So the permutation group of 3 points is generated by Z goes to 1 minus Z and Z goes to 1 over Z. It's got some fixed points. Z goes to 1 over Z, fixed point is 1. It's got some other, there are other fixed points, minus 1. Okay, and those are the ones that become the pinched points. So we saw that a dessin can just be seen as an unramified cover of P1 minus 3 points. But then it's also a cover of this thing here. And that, it's easy to confuse the two things. They work exactly the same thing and they're similar, but that's going to turn out to be very important for what Grothendieck was trying to do, which I will show you next. Okay, so that fact that you can see this is a cover of H mod gamma 2, but also H mod PSL2, it has an arithmetic, it has a very important arithmetic consequence on the Galois action, on letting us see what the Galois action looks like. Okay, so I'm now getting to the key point of what I'm going to explain to you what it was that Grothendieck was trying to do with this. And then the last part of my talk, I'll get a little bit more ambitious and try to give you the really big picture of what he was hoping to do and where we're at now. Just checking the time. Okay. Okay. So as I've already said several times, this is what Grothendieck was excited about. He saw Dessins d'enfant as codes for which encoded in a very short way, the huge amount of information contained in a Bialy cover with a Riemann surface defined over Q bar, curves that map the ramification, all of that. Okay. So we saw this already. It acts on them for all the reasons that we saw. But it acts on them because, okay, this is defined over Q bar. Let's talk a bit more about how it acts on Dessins viewed as subgroups of the free group on 2 generators. So here's another one of those quotes from the Esquisse. Since finite maps, again, finite maps are Dessins, they can be interpreted as coverings defined over Q bar of an algebraic curve. This is Galois Q bar over Q. That's his notation for Galois Q bar over Q. So it acts on the category of the Dessins, and he makes some remarks about it. And here's the very Grothendieck-like observation. Here then is a mysterious group, Galois Q bar over Q, intervening as a transforming agent on the topological combinatorial forms of the most elementary possible nature, leading us to ask questions like, are such and such oriented maps, these are Dessins oriented maps, conjugate, or what are the Galois conjugates of a given map? Visibly, there's only a finite number of these. Okay, clearly he saw, that the ramification indices are preserved by the Galois action. So here's the thing that I was wanting to show you before, where you have to realize how extraordinary this sentence is for Grothendieck to write. I considered some concrete cases for coverings of low degree by various methods. And this is just something that he waited until the 1980s to just take out his pencil and try some concrete examples by himself. He was also helped by a couple of students. I doubt there's a uniform method for solving the problem by computer. Yeah, well, we've seen people doing their best to work on this problem, but no generic solution. My reflection quickly took a more conceptual path, attempted to apprehend the nature of this action of Galois Q bar over Q. one sees immediately that, roughly speaking, it's expressed by a certain outer action of the group on the profinite fundamental group of P1 minus 0, 1, infinity. Okay, so now we get to the point. It's easy to say Galois group acts on Dessins. We saw why. We know why. Dessins correspond to finite index subgroups of the free group on two generators. We understand that too. Therefore, there's a Galois action on the finite index subgroups of the free group on two generators. But why? How does Galois act on that? Why? How can we express that directly? So that's what I'm going to show you now. It's not complicated. Here's how it works. You take your Bialy cover. Let's just assume it's Galois. So it's a quotient of this is the upper half plane. I forgot to make it boldface by gamma 2, by a finite index subgroup, by a normal subgroup. That's just a convenience. There's no absolute necessity for that. Okay. Now you look at the function fields. Here's the important trick. You're going to look at the function fields. The algebraic function field, the Riemann sphere, we've got ramification here only over 0, 1, and infinity. So the function field we're going to look at is just C of t. This is just a notation for the algebraic function field of the Bialy curve. Now, if you've got an extension of function fields and they're defined over C, but your curves are defined over an algebraic closed subfield of C, which is the case here because they're defined over Q bar, then you can take the extension of function fields defined over that algebraically closed field, which here is Q bar. It's not going to change Galois group. This is a very important theorem, very useful and use it all the time. You can, as long as this is an algebraically closed subfield on which everything is defined, the Galois group of this field extension is not going to change. So let's stop looking over C. Let's just look over Q bar. What do? You take this function field. You take all the Bialy covers, all of that. They all have a function field where we're using this notation. Take the compositum of all of those together. What are you getting? What's the Galois group of that huge thing? What is it? Well, one thing you can say is all its finite quotients are these finite quotients. But these finite quotients are the same thing as gamma 2 mod the normal subgroup H. They're the same as the finite quotients of gamma 2, the same ones. So here you have an inductive systems of all these finite groups G, which are the finite quotients of this discrete group, which is free on two generators. And that is nothing but the profinite completion. That is exactly what it is. You simply take the full compatible system of all finite quotients of a discrete group, and what you get is a group, I'm calling it G, that is profinite as a topology, but otherwise it's extremely similar. This one sits inside it, and it's generated freely by two generators, only it's generated in the topological sense. However, there's a big advantage to using the profinite completion instead of the discrete pi one. And here's what it is. We have this field extension K of Q bar of T, and it's got this big Galois group G. But Q bar of T contains Q of T. And that has Galois group Galois Q bar of Q, just acting on the coefficients of the functions. So now we have a tower of three. We've got Q of T, Q bar of T, and the big guy K. Here we have Galois Q bar over Q, and here we have that big profinite Galois group G. Anytime you have a tower like that, the lower part has a canonical outer action on the upper part. So now we have a canonical, we have to understand completely. There's a canonical outer action of this on that profinite group G. Now the quotients, the finite quotients of G are exactly the finite quotients of gamma 2. So literally by definition. Therefore, the finite index subgroups of G are in one-to-one correspondence with the finite index subgroups of gamma 2, even though this is a topological group and this one is discrete. So you can just as well say Dessins correspond to finite index subgroups of this. But there's a natural outer action of the Galois group on this. And that's where your action is coming from. This is a completely different way of viewing the Galois action on Dessins. You don't have to calculate the equations anymore when you do it this way. And the fascinating thing, which I'm leading up to in the rest of my talk, is that this lets you say stuff about the Galois group that has never been formulated before in any other way, because nobody ever tried to look at it acting on the group like this. They always look at it acting on algebraic numbers. So we're identifying P1 minus 3 points as the quotient of the upper half plane by this free group on two generators. And this is a discrete group. So let's talk about the discrete pi1. It's just, you take a base point somewhere and you have 3 just loops on the sphere around the 3 missing points, X, Y, Z. But the product is 1, right? So it's really a free group on 2 generators. You really only have to look at X and Y. But if you want to keep all the symmetry, you look at X, Y, Z with a product 1. So that's how gamma 2 looks. And G looks exactly the same, except we're talking about generating in a topological manner now. So whenever you have Galois action acting on these extensions of function fields, this is maybe one of the most important. This is it's a classic feature, but it's also like it's an automorphism of the profinite fundamental group, but not just any automorphism. The Galois action always preserves conjugacy classes of inertia groups. This is like the fundamental Galois feature. You might even ask yourself, take any variety defined over Q bar. Take its fundamental group. Take the profinite completion. Take the whole automorphism group of that group that respects the inertia groups. Is it always the Galois group? Maybe it's always the Galois group. We don't know. It's possible that this feature of the Galois action is so powerful that it actually tells you who the Galois group is. Now, that's an open question that I'm asking now, okay? However, what does it mean to preserve conjugacy classes of inertia groups right here for this group? It simply means that the elements themselves are conjugated and by an element of the group and raised to a power, because they have to land in the same conjugacy class. Okay, so since we only have a canonical outer action, we're going to raise it to an actual automorphism action, but in a non-canonical way. We're just going to say, lift it anyway, and then conjugate, use the inner automorphism by whatever's conjugating X. So this is just one possible lift up to inners of the canonical outer action. X is just raised to a power, but Y is conjugated by somebody. Z is also conjugated by someone, but we don't care. We're going to ignore it. We only need to know X and Y because they're the generators, okay? It's very easy to see that the powers have to all be equal. A priori, you could think they could be 3 different powers, but you just pass to the abelianization, which of course the Galois action respects. And the only way you can get X, Y, Z equals 1 is under the Galois action is if all 3 powers are equal, okay? So forget Z, we don't need it. The Galois action looks like this. So it's not hard when you look at the abelianization to see what lambda is. It's just the cyclotomic character. The cyclotomic character is just what tells you how an element of the Galois group acts on roots of unity and only roots of unity, nothing else. In other words, lambda encodes the Galois action on the abelian extensions of the rationals. It's the most trivial part of the Galois action, essentially. So what that means is that all the really complicated part of some element of some arbitrary element of the Galois Q bar over Q is contained in this little guy here, F. But where is F? F is in the free group on 2 generators because this is a conjugate of the element inside that group. So what are we saying here? Where's it saying? You have just the power lambda, which is well understood. It's a cyclotomic character, and you have an element F in the profinite free group on 2 generators. And that is giving you, that is encoding completely the element sigma of Galois Q bar over Q. Now, nobody knows how to write down an element of Q bar over Q, Galois Q bar. Nobody knows how to write down an element. It's a profinite group, we don't know, except complex conjugation, which is, if you want to know what it's like in terms of lambda and F, it's lambda is -1 and F is 1. So that's the only element we know how to write down. Now, you might tell me, well, we don't know how to write down an element in the profinite free group on 2 generators either, because that's infinite too. I'm okay. So it's not that we can just write them down. But I don't think anybody will dispute that the structure of the profinite free group on 2 generators is a lot simpler than the Galois group. And what we're saying is, inside the profinite free group on 2 generators is a bunch of elements F coming from the Galois group in this way. So
Grothendieck, 2 elements F and G, no? In the previous equation.
Yeah, but you don't need G. It so happens because Galois always preserves inertia, that it does this. But in fact, the group's generated by X and Y. So if I give you the image of X and Y, that's all you need to know to get sigma completely.
Okay.
G just comes for free. So what did Grothendieck say? One of the most fascinating tasks here is to discover necessary and sufficient conditions on an outer automorphism of G. So an outer automorphism of G, or which you can lift to an automorphism that has to look like this. On the corresponding parameters, parameters are what he calls the lambda and the F, which would give a purely algebraic description in terms of profinite group with no reference to number fields of the absolute Galois group, Galois Q bar over Q. This is a very important slide. This is kind of the key slide of my talk. This is what Grothendieck was getting at with the Dessins d'enfant. A finite index subgroup encodes the same exact thing as a dessin. It's a finite index subgroup with a free group onto generate something very simple, encodes a dessin in a finite way, but we have this natural Galois action on it. And so let's see what it tells us about the Galois group. So first information that we have, any element of the Galois group is just given by this pair lambda and F. And that comes from Dessins d'enfant, if you view them as subgroups of the free group onto generators. Now I'll give you a second necessary condition, and then I'll get to the very last part of my talk, which is kind of high flying and shows you the big generalization that he had in mind. The second one comes from this PSL2 of Z. So I showed you before that if we can also just as well consider a dessin as a cover of this pinched sphere that you get when you quotient the Poincare upper half plane by the whole action of PSL2 of Z. The fact that you can do that is going to tell us something interesting about these elements lambda and F in this incredibly explicit way. So I'm just going to show you that. So I take two standard generators of PSL2 of Z. So before I showed you the generators called S and T, and I'm just showing you here that here's how to write them in terms of these tau ones. And the squares of these are two standard generators of the free group on two generators. Okay. All right. Here's a statement which I'll prove a little lower down. We know the natural Galois action on X and Y, which is T1 squared and T2 squared. So it could seem completely natural that I tell you if you take T1 instead of T1 squared and T2 instead of T2 squared, the action is the same. Okay, it needs to be proved, and I will prove it a little lower down. But let's just accept it for now. It acts this way. But, and here's what's very cute. This is something very important. There's a difference between gamma of 2 and PSL2. Gamma of 2 is a free group. Once you've said how you act on the generators, you have nothing more to say. But PSL2 is a group with relations. So once I've said how you act on the generators, you've got to make sure your relations are satisfied. This is what Grothendieck was so excited about. Here are the relations. You have an important element of order 2, an important element of order 3. Those are the relations in PSL2 of 3. So you calculate their images, and you calculate this, and you use this condition to get conditions on little f. And here you have a condition on little f. F times theta of f has to be equal to 1. That comes if you calculate out this action on this element and you square it. You get this property of f. F has to have a property. Theta is the automorphism exchanging x and y. It's the automorphism. So f is in f2, theta exchanges x and y, and the product of f with theta of f has to be equal to 1. That's a really concrete and a strong property on that element f. And here's the second property. This one is a 3 cycle. Comes from this 3 cycle here. F times x to the m is just lambda minus 1 over 2. F times x to the m times rho of f times y to the m times rho squared of f times z to the m is 1. Rho is the 3 cycle automorphisms, x to y, y to z, and z to x. Okay, so these are just 2 finite, simple properties of f that arise simply because Dessins are Galois covers of H mod PSL2 of Z. And Galois acts on PSL2 of Z. And it permutes, it acts on all the subgroups, it permutes all these Dessins, and the action is giving us this information. So Grothendieck was very excited about the fact that you can parameterize elements of the Galois group. He calls them parameters by this lambda and f, And he wanted to find necessary and sufficient conditions. And what I've shown you here from the very first situation with PSL2Z is two necessary conditions. Okay, and now I'm on to the end of the talk. Check the time. Oh my gosh, I'm sorry. I'm going over time. Is that okay?
Yeah, okay.
Yeah,
Between 15 minutes.
I mean, I'm kind of the end here. It's going to be a bit more free.
No, you can take 15 minutes. Yeah.
Okay, I'll just go on until I'm done. It's not that long. But I want to say, the last thing I want to say that is really, really important is you have to be Grothendieck to have this idea. So where do you go from here, right? We're all looking at this and we're all like, oh, wow. He got these lambda f, that's incredible. And he even has a couple of necessary conditions on lambda f, but of course they may not be enough necessary conditions, we don't know. Where do we go from here? I mean, you can look at any variety defined over Q bar and it's going to have a fundamental group and you can take the profinite completion and it's a Galois action, but you don't know how Galois acts on the generators at all. So this isn't going to help us with that. So how are we going to get more conditions on lambda f? And here's what Grothendieck did. This is one of those ideas that I think very few people would have had, and you really have to have his way of thinking to come up with the idea that he came up with to answer that question. So the natural outer action acts on the profinite free group 1-2 generators, permutes the finite subgroups, everything's completely topological. How do you generalize it? Here is what he said. He said, we're going to look at moduli spaces of Riemann surfaces. So what are the moduli spaces of Riemann surfaces? They're just spaces where every point corresponds to an isomorphism class of Riemann surfaces with genus G and a certain number of marked points. So we already saw this, one example of this, because I already showed you that this space here, that folded pinched sphere with ramification indices 2, 3, and infinity, the quotient of the upper half plane by the triangle group 2, 3, infinity, is identified with the moduli space of elliptic curves. Every point in that fundamental region is a J invariant of one isomorphism class of elliptic curves. So we've seen one moduli space. It's that pinched looking sphere with one hole and then elements of 2 and 3, 2 points with ramification indices 2 and 3, which correspond to the elliptic curves with special automorphism groups. Okay, so we've seen a moduli space. It's M11. Elliptic curves are nothing but genus 1 curves with 1 marked point. We've seen a second moduli space. P1 minus 0, 1 infinity is a moduli space. It's a moduli space of Riemann spheres with 4 ordered marked points. So you just pick 4 points. They have to be distinct, right? So just pick any 4 points on P1. Now we want isomorphism classes. So we look at the isomorphisms, the automorphisms of P1. This group acts triply transitively. So there's always a unique element of it that will take your first element to 0, the second to 1, the third to infinity. And then we just look at where X4 goes. It goes to some element, we'll just call it tau. It's a cross ratio of the others, actually. So P1 marked with these 4 points is isomorphic to P1 marked with 0, 1, infinity, and this new value tau. These 4 points have to be distinct. So tau is different from 0, 1, and infinity. So what that means is, just give me any value of tau different from 0, 1, and infinity, and I'll give you an isomorphism class of P1 with 4 marked points. So P1 minus 0, 1, infinity is a moduli space. It is the moduli space, M04, of Riemann spheres with 4 more marked ordered points. And a point on here, tau, corresponds to the P1 marked with 0, 1, infinity tau. So we've actually already seen 2 moduli spaces. And what Grothendieck now says is, let's look, what am I doing here? Oh, let me just say, yeah, this is important. Before I move on to the other moduli spaces, this is a good point. We already saw this. We have this short exact sequence. In fact, S3 permutes the marked points. So we could view this as being 4 ordered marked points to 4 unordered marked points. But giving 4 unordered points is the same as giving an elliptic curve, okay? If you know the 4 ramification points of an elliptic curve, then you know the elliptic curve. So that shows you why this mapping to its quotient by S3 is identified with this mapping to that quotient. This is P1 minus 3 points, the moduli space M04. This is the moduli space of elliptic curve M11. So what we've got here is a very nice map, completely defined over Q, because this has 3 actions defined over Q, between 2 different moduli spaces. And the map is defined over Q. And we saw that the Galois group acts on the fundamental group of this profinite and the fundamental group of this, but it also respects that map. And that is the proof, in fact, of this fact here, which I said I would prove a few slides lower down. But you have to have the compatibility of the map in here. The compatibility of that map shows that when you take the map on here and you have restricted to here, you have to get the one that we said, okay? So what Grothendieck wanted to generalize is, firstly, we looked at M04 and M11. Why not look at all the moduli spaces MGN for all Riemann surfaces of genus G with n-ordered mark points? Secondly, we were only looking at things that come fundamentally, essentially from topology. He wanted to look only at the maps between these spaces that come from topological actions on the underlying topological surfaces. So, and the second incredible intuition, I find this just amazing, is the existence of a 2-level principle. So he says, let's look at all the Riemann, all the moduli spaces for all G, all N. But then he says, you don't actually need to. All you need is to look at the dimension of these spaces equal to 1 or 2. So the dimension is 3G minus 3 plus N. So the 2 spaces we've already seen are of dimension 1. They're just P1s. There are 2 spaces of dimension 2, M05, spheres with 5 mark points, and M12, which are tori with 2 mark points. And he says, if you take these 4 spaces, take their 4 pi ones, take the profinite completions, take the canonical Galois actions, and furthermore, you add all the maps between these spaces, not all of the maps, not all possible maps. No, specific maps that I'll tell you about, which are purely topological and come from topological surgery on surfaces. Then you don't need any of the other GNs. Every single thing with all of the other GNs will be automatically satisfied. You won't get any further information from them. And the reason for this is because big things are built up by many little things stuck together. That's the game of Lego. And that's the last thing I just want to explain to you. It's such a beautiful idea and it's complicated. So I'm going to go over it pretty quickly, but it's just such a beautiful idea and I want to show you how it works. So the first, this is where he says this 2 first levels of the tower. The entire tower, so the tower, it means all the moduli spaces for all G and N with all the maps between them, but not all maps between them, the topological maps between them. Here he says what they are, the operations of gluing, and there's somewhere else where he says the operations of erasing. We're just going to look at those 2 maps, nothing else. This is all you need. This is an intuition, he says. He says, I don't know how to prove this, but I'm absolutely completely sure it's true. There's an analogy between what happens for reductive algebraic groups. It becomes even more striking if he identifies T11 with SL2Z. He doesn't use PSL2Z for a delicate reason, which I won't get into here. In a word, when he uses SL2Z instead of PSL2, it's because he's taking into account the fact that every elliptic curve has an involution. So it's really an extension by plus or minus 1 of PSL2Z, but it's a detail. He's saying this group is the fundamental building block for the whole tower. And that's the same thing as what happens when you look at reductive groups. And he says this group is absolutely essential. And all of this is intuitive because he says elsewhere in the text that basically, I don't know how to prove this, but I'm completely sure it's true. So he was completely sure. And so he started to concentrate hard on these 2 moduli spaces, which he believed would be the ones that would give all the information. And this again is a quote. So the modular multiplicities, this is what he calls moduli spaces. They're practically isomorphic. They're very similar. Appear to be virgin territory. Bray groups will not enlighten us on their score. Now that's really interesting. The Art and Bray groups are the 5-strand Art and Bray group is very similar to the pi 1 of this. It does enlighten us. But he has many reasons for saying, yeah, but it's not enough. It's not enough. We've got to do something much more subtle and complicated than that, which I'll tell you in a minute. I've been going to look at M05. It's a real jewel. It is a rich geometry closely related to the icosahedron, but it's absolutely not like the icosahedron. It's a very beautiful special space. Okay, so where's the topology in all this? Why do I keep repeating that he wanted to look at the Galois action on topological objects? So the fundamental groups of these spaces are very well known. In G0, they look very much like the Art and Bray groups. The Galois action on these, always profinite completions, we saw it has to preserve the inertia groups. The inertia groups are generated by certain diffeomorphisms called Dane twists. So let me just tell you what a Dane twist is, just so you see that it's really topological. Just imagine a cylinder, just a cylinder. Draw like a loop around the belt of your cylinder. Now twist the whole thing by just one complete turn. So let's say you hold one end of your cylinder still. You make the other one go all the way around so that the end edge is up exactly where it was before. The diffeomorphism is a Dane twist along the loop that's called a bell, that simple closed loop in the middle. It's just a simple twist around a loop. It's completely local. You can draw any loop on a topological surface, cut out a little cylinder neighborhood, do that thing, glue it back on the borders. And it's a completely topological little twist. And those are what the Galois action must preserve because those are the inertia groups. So here are the maps between moduli. So now we know something. We know these groups. We know there's a canonical Galois action. We know that action respects these twisty things. What about maps between the moduli spaces? Here are the maps he wanted to put. Well, the really easy one is where you just erase a marked point. That's really easy. You have n marked points. You erase one of them. You go down to him. That's a very simple topological action. You erase a point. And it goes between these two modes. Those have to be respected by the Galois actions. But here's a really interesting one that got him so excited. Take your topological surface and draw a bunch of disjoint closed loops on it. Any number. You can draw one, you can draw as many as possible. You can draw the maximal number. Doesn't matter. Cut along them. Just cut. Then you can view it differently. You can view that you take all the pieces and glue them together. That action of, you can consider it as either cutting or gluing, gives really important maps between the moduli space, very special maps between the moduli spaces. And those are the maps that he says, when you look at the fact that Galois, they're defined over Q, the Galois action has to respect those maps, and that's going to give us a bunch of information on the parameters lambda f. So here's the quote that he says. We have these 12 fundamental building blocks. I would like to know more, tell you more about this, but I basically you have two choices. You have the small box of Legos is reduced to the identical blocks of type 03. So here are the blocks. So when you cut, look at this piece right here. This one here is a pair of Thurston pants. It's just a sphere with 3 boundary components. It's just the same as this. If you put enough loops on your surface, you'll cut the whole thing into just Thurston pants. And that's what he calls the smallest box of Legos. You've got only all these blocks of 03 and you glue them all together and you can make every surface that way. And that's how he says you build everything from these little pieces. But you don't have to do that. You can also put less loops on. Like here, there's a genus 1 thing. Oh, well, no, I guess he did cut this. But suppose you don't cut it. Suppose you don't. Then you have something of genus 1. And he wants those to be pieces too, but not any. Only the ones with automorphisms. So that's the big box. But if you just take the smaller box, you put as many loops as you can on a surface and you cut it all into pieces like this. And he says, when you put them together like this, he calls it, they're building blocks which can be assembled by gentle rubbing as the ordinary game of Lego dear to our children or grandchildren. Okay, so I don't see them as Legos. I see them as this game. My grandson has this game. This is a really cool game. You can build anything. And I really like this picture because if you look at it, okay, there's a mistake because it's got cylinders. We shouldn't allow any cylinders. But we should allow, what he wants to allow is things like this. This is a P1 minus 4 points. This is a Thurston pants right here, okay? There's none of genus 1, but we could allow some genus 1 too. So this is really the image he has in mind, where you build up any surface topologically by these little pieces, but when you put a Riemann structure on it, they all have a Riemann structure. So the P1 minus 3 points don't have any interesting Riemann structure. It's unique. But the more complex ones have different Riemann structures. So I'm just going to tell you very, very quickly now how when you glue pieces together like this or this, when you glue the pieces together, why that gives you a map between moduli spaces. So it's pretty easy. I'm just going to give it an example to visualize it. The best is an example. So let's just look at a sphere with 5 mark points. So visualize a sphere with five mark points on it, 0, 1, infinity, x and y, up to isomorphism. This is a unique representative. So what's the moduli space? The moduli space is given by all pairs x, y, and p1 squared, except x can't be 0, 1, infinity, y can't be 0, 1, infinity, and x can't be y. So you've got to, from P1, you have to remove 7 lines, and that is the moduli space, M05. It's really pretty. Now there's a compactification here, which consists in adding what you call stable curves. So to see what the stable curves are, you allow the points to be not all distinct. What that means is, in a specific way, in a stable way, is you number the points are numbered 1, 2, 3, 4, 5. Draw a geodesic around 2 points, say 1, 2. Just draw a circle around 1, 2. And you keep using, you keep modifying your hyperbolic structure. You're traveling on the moduli space in such a way that this geodesic gets smaller and smaller and smaller. And in that sense, we say the points are closer and closer. And at a certain point, the length of that geodesic that's surrounding your points 1 and 2 becomes 0. You pinch, you've got your balloon here and you pinch it in the middle. You've got 2 mark points on this side, 3 mark points on that side. And what Deligne and Mumford did to compactify the space is they added that. It doesn't really count because it's not really a surface. It's got a 0 length geodesic, but it's added to make the compactification. That's how it's made. Now, what is the moduli space of that? The moduli space is the moduli space of the piece P1 minus 3 points, but that's just 0 dimensional. It's just the dot. And here you've got the P1 minus 4 points, and that's a 1-dimensional moduli space. So in order to compactify, what Deligne and Mumford are doing, they're adding all the points that you obtain pinching this way, which forms a line, a 1-dimensional thing, and you add that line to your moduli space. But there are 10 of them because you've got 5 points and each pair creates such a line. 1, 2, 1, 3, 1, 4, each pair creates such a line. So you take 7 lines out of P1 to get the moduli space, but to compactify it, you add 10 lines. That's a very, very funny and interesting space to look at. Geometry is really fun to play with. But the basic fact is you take a P1 minus 3 points and you take a P1 minus 4 points and you attach them. And you get a stable P1 minus 5 points. What you're doing is you're sending the moduli space of those 2 pieces, but really only 1 piece because P1 minus 3 points is just a point, to one of these lines that's in the compactified moduli space. And that map between moduli spaces, which is defined over Q, gives a very, very simple map between the pi ones of these moduli spaces. Very simple. Now I'll show you that. It's actually simpler to see the map between the pi ones than between the spaces themselves. Let's suppose I cut along this curve here and I glue this piece to the rest. Well, so the fundamental group of the moduli spaces, I explained to you that it's generated by Dane twists along simple closed curve, by twists. So the twist along this simple closed curve is going to map to the same thing, the twist along this simple closed curve. But first, you consider it as included in this piece, and then you consider it as included in the whole thing. It's a really simple map. If you just associate generators of the fundamental group to these loops, the inclusion becomes completely obvious. You've got a very simple map between the fundamental groups. All right, and the last thing that I want to say, which is really the whole point of everything, is you now have all these moduli spaces, all their fundamental groups, all these Galois actions, and all these maps between them that I just described. Only you don't have to look at them all because he says you only have to look at M05 basically and M12. And when you do this explicitly, you will get further conditions on the parameters lambda f. And the most famous of these conditions is the super famous 5-cycle relation, which Grothendieck did not find. It was actually discovered and written out explicitly by Drinfeld. And it happens. So what is the fundamental group of M05? It's very close to the braid group. generated by these things, which are just crossing braids. And there's an element of order 5 inside this fundamental group. What? The 5th power is equal to the set, just basically of order 5. So it's not surprising when you act on that element, it multiplies itself by an F. And when you take it to the 5th power, it gives it, it's very similar to what we had before. It's very similar to what happens here. The little term with n doesn't appear. But here, we had this, this automorphism that said x to y, y to z, and z to x. And this turns by that automorphism. And the exact same thing happens here. You've got a 5 cycle, an element of order 5, and you just keep applying it. And these 5 things go all the way around, and that has to be equal to 1. It's essentially a reflection of the element of order 5 that's in there. So now comes the really fascinating, very last remark of my talk, which is, if you take all the automorphisms of the free group on 2 generators that look like this, and you ask for these three, you have a group, it's called a group, it's a Grothendieck-Teichmüller group. And the major open question of Grothendieck-Teichmüller theory is whether that group is enough, whether that group is the Galois group. Do we need anything further? Maybe one simple remark is I haven't used M12. And if you use M12, you can get 1/4 relation here that looks like this. Some people believe that even that is not necessary. The reason being that M12 is extremely similar to M05. Other people believe that it is necessary. I like it. I would like to add the 4th one. It doesn't really matter whether you write the 4th one down or not. The fundamental question remains. What is certain is that you don't need any other G and N. You don't need any other genus or number of mark points. These 2 levels, the 2-level principle, they give you all the information that this topology is going to give you on the absolute Galois group. But is it enough? Is it enough? Is it possible that this group, with its incredibly simple description, could be the absolute Galois group? So this has been basically the subject of my research since about 1991, when I first started searching for Grothendieck and reading the Esquisse. I don't think we're still that near to an answer, but hopefully in my lifetime, it would be great if somebody proved that. That's my talk.
Yeah, thank you very much, Leila Schneps. Yes, very nice talk. There is not much time, but maybe any quick question if there is any. Otherwise, we'll go to the next talk.
Yeah,
So,
sorry, I really did run over.
No problem, because it is very nice talk and this much time was required.
I think we should invite her again.
Yes. Yes.
Can I ask a question?
Yes, please. I think please proceed.
So there is a precise conjecture of what the F's are. You wrote down that automorphism.
This one here?
Yeah, the automorphism X goes to X to the power lambda and Y goes to F inverse Y lambda F.
Right.
And the question is, what are the F's which come from the Galois group of Q
So
bar
let me
over
say a
Q?
conjecture, but I'm not even going to say I believe in this conjecture. I don't know if it's true or not. Let me say the conjecture.
Mhm.
Every F in the profinite group on 2 elements, which satisfies 1, 2, and 3, comes from a Galois element. In other words, these necessary conditions are also sufficient. That would be the conjecture. And there's various different versions of this conjecture, but that's the essential nature of it.
They must satisfy 1, 2, 3 is certainly the case.
They're necessary, but are they sufficient?
Okay.
Yeah, that's the question. I mean, what's certainly true, I can tell you, is the Galois group is contained in here. And in fact, I actually proved an interesting result that I was very excited about, but I didn't get anywhere with it, which is that if the Galois group is normal inside this group, then they're equal. And you think it would have to be normal, because how canonical can the Galois group be, right? You'd have to be normal, but I can't prove it. And I did this like 20 years ago, and I haven't made any progress with it since. So, yeah.
Action of the Galois group on the outer automorphism group is faithful.
Yeah, that is correct. Sure.
And
it's
that
faithful on Dessins, right? We saw that already.
That is maybe elementary observation. Faithfulness of the Galois action on the outer automorphism group is that simple enough?
Yeah, well, it's not utterly trivial, but it follows from Bialy's theorem. I think it was said in one of the talks, right? I think that Claire Burlin said that. Yeah, you can prove it by using Bialy's theorem. It's not trivial.
Okay. Oh, it's a consequence of Bialy's theorem?
Yeah, or else you can do it in different ways. You can always find an explicit dessin on which everything for a given element of Galois, you can construct an explicit dessin where it acts non-trivially.
So the Galois group is a subgroup of the group that you define, and
that is correct. That is correct.
You don't know it is a normal subgroup?
No, I don't know, but I do know that if it is a normal subgroup, then they are equal.
Why?
And it just seems so weird to think it wouldn't be a normal subgroup. Oh, the proof is not that hard. It has to do with the complex conjugation being very special. Complex conjugation is self-normalizing in this group, and it's also self-normalizing in the Galois group. So there's no other place it could go. That's the gist of the proof. But you can't even imagine how Galois could not be normal, but I still can't prove it.
Okay, so thank you very much. So we'll stop this talk now, and any further questions may be return to Leila Schneps by email.
Yeah, sure.
Yes, thank you.
Thank you very much.
Yes, thanks a lot for coming. And
pleasure.
Let us have one more talk, as Rabindra Kulkarni has suggested. So now we'll have a break of 10 minutes, and then we will have.